pathways, and then there are multiple things that show up in your spectrum. So simply looking at a different linear combination allows you to get the information that you want. It's a change of basis set and nothing more. There is no physics in the dynamic Feynman pathways that is not already in Schaal-Mukamel's formalism. It is merely a change of basis to be more natural to understand what's in your spectroscopy. But it's highly enabling as you watch different features do different things in your spectrum to extract, say, population dynamics, the chemical kinetics that are behind these changes, whereas they show up throughout the Feynman diagrams as written by Schaal. So I should be very clear that there is no physics. There is nothing beyond what Schaal has done except taking different linear combinations of his diagrams in a clever way, which is what Ham and Zani look at with their dynamic Feynman pathways. But it's an interesting organizing principle. So there is no reason you can't do it with coherences. It's merely a change of basis, but I did not do that in this talk.
But do you have evidence in your experimental results that this might happen?
So we are looking at the quantum beating signatures now in another data set, and we do see changes between the different oxidative conditions, and we're trying to get good enough signal to noise that we can publish that. So it's hard for me to say exactly what we see or what we have evidence of, but we are seeing differences and we're digging into it. My student, frankly, thought they had a smoking gun, and I found some statistics issues in their analysis, and we're going back to really make sure that that which is signal is really signal. And we have to be very careful about this, as I'm sure everyone appreciates. We want to get it right.
What you do with this mutation is really to change the resonance between vibration and electronic state. I understood correctly.
Yes, that is what we're saying this vibration does. Yes, that this mutation does. And in fact, it's not merely the mutation, it's also the chemical change to that particular cysteine residue. So it's a thiol, SH, and then it becomes a thioradical, S dot, when exposed to oxygen. And then if you mutate it to an alanine, it's chemically inert. Nothing happens upon exposure to oxygen.
Mm-hmm. Very nice. It was very stimulating talk.
Thank you.
I encourage in particular, I mean, students and young members, right, to pose questions to our speakers. I mean, it is not often that you have the occasion to have speakers available for me of this reputation available for you. Oh, I see a hand by Ksenia.
Yes, hello everybody. Thanks a lot for very nice lectures. I enjoyed this afternoon so much. So I have a question to Daniele. You said something about that you have high resolution in time, but your resolution and frequency is determined by these peaks. Can you tell a little bit more of how this peak broadening is defined in the way how you define the random? And then is it like, what does it mean for theoreticians? Is it that decay is better described because it's in time, highly resolved, or like how bad is this bad resolution and frequency in some things that we typically discuss? Thank you.
Yeah, so it's a little bit like, as I said, a little bit like this femtosecond Raman, where you use like a narrow band local oscillator and a broadband pulse, and you make them interact. So the idea is that if you do, so let's say first experimentally, the width of the correlation is determined artificially by the resolutions of our shaper, basically. So in the classical fluctuations, we included artificially an amplitude and phase noise, which has a certain width, which is defined by the resolution we wanted to achieve, which in our case was like 1 terahertz in resolution. But then when you do the mixing, basically, when you do the scattering process, you take one photon from the coherent part and one photon from the incoherent part. You can say it like this. And your pulse is basically in time, will have some longer tails. But if you look at the observable of just looking at the correlations, basically you kick out everything else and you remain with a correlation signal, which has a frequency resolution, which is the width of your correlation in the stochasticity you implemented, and the time resolution, which is instead is the bandwidth of your starting pulse, the inverse of the bandwidth. Yeah, so of your starting pulse. So in the I haven't discussed much because we haven't published this, but basically, if you do it in the time domain, you can see that you can select one specific process just by taking your pulse and shaping it so that you have stochasticity on one side and you have instead a flat profile on the other side. And by doing so, you select which process dominates, whether you dominate with a blue shift or a red shift. And we see that in this case, the correlations evolve and we have resolutions, which is sub-cycle resolution in the correlation. So we see the evolution in time of this scattering process, which evolve in an intelligible way within like one period of the phonon oscillation. Actually, maybe there was a part which I didn't explain what was, but I mean, I'm pretty sure that for this community is relatively trivial, that you can have like at least I come from the condensed matter side, and for us it was not trivial to recast. So coming from the condensed matter side, we try to see the phonons in the phase space. So basically you write them as a classical harmonic oscillator. Okay, and then you have a scattering process which maps the position of the atoms, because for us we have basically the way our simplified language, you just expand the susceptibility of your object in terms of the phonon coordinate. So the maximum expansion or compression along the phonon coordinates give you the maximum modulation of the refractive index of the object, while you have a scattering process which comes in at the same order, which mixes instead frequency components, and that's maximized at the maximum of the momentum of the phonon. So it's a little bit cumbersome. Maybe I can I show an animation, Elisabetta? This will be, can I show something?
Yes, let me just make you, okay. You should be able to
yeah. Yeah, maybe you're seeing, you should be seeing my representation right now. So a good representation, I mean, this is like in non-resonant conditions. So let's say purely, it's a transparent crystal. For us, there's no electronic states in between here. So we just have a purely virtual process. So the system is quartz, is non-absorbing. Okay. And the description we do, you find it, because for us, we are trying to go with this correlation thing towards the quantum limit, because the uncorrelated fluctuations in frequency will dominate when you are in a photon limit. So it will, for us, it was important to develop this formalism, but we did nothing but rewrote the classical formalism just using operators. That's a bit, probably a bit redundant, but still for us, it was necessary to define what we can expect when we go to very low intensity. And the idea, I think a good representation could be this, where we basically use the phase space representation for the phonon, and we write what the interactions, both in the pump and in the probe. So again, this is a simplified way of rewriting the nonlinear response. But basically, you can say, if you write it in the phase space of the phonon, you can say that the pump imprint a momentum. You can write, you find the Hamiltonian description here, but basically you can imprint a momentum on the phonon coordinate, and you do so by the redshift in the pump. in transparent limit. So this is there's no electronic states here. And then as the phonon evolve, okay, you can come in at different times and different process which comes in at the same order. One which is just let's say the modulation of the electric function as in terms of the phonon coordinate. And if you come in at the maximum of the position or minimum, depends which side you look at, you can you see that your scattering process doesn't do much to the phononic states. It doesn't increase the energy of the oscillations, and you have an increased transmission, while you can come in out of phase and you have a decreased transmission. And this is one process. Okay, one process which basically doesn't change the frequency content of the probe pulse, but it just modulates its intensity. And that's maximized by the phonon position, by the atomic position. On the other hand, and this is basically, so this is from the experimental point of view, this is relatively trivial. So this is just the modulation of the transmittivity in time. While on the other hand, you have another process which is instead maximized by the momentum. And basically, this is the real Raman process where you exchange a quanta of excitation, so to say. And if you want to represent this in the classical limit, in the phase space, you basically come in when the momentum is maximum with your probe. You change the motion status of the ion, and you get again a redshift of your probe pulse. And this can happen in the opposite limit when the momentum is maximally negative, and you do a tiny quench of your coherent state on the phonons, and you get a blue shift. So this is basically a process where your transmitted probe wiggles blue and red. Okay, and you can select this just if you do intensity, you can select this in a different with selecting polarizations, and you see that basically it's your coherent response is a blue and red shift of the probe pulse. Okay. So the four processes are those. And when you select, you put yourself in a situation where you have maximized this second process. This is what happens in the correlation measurement. That if you shape your pulse so that you have stochasticity only on one side, and you leave your phase flat on the left side, you can select a process where the frequency coming in is smaller than the frequency coming out, and your cross correlation is dominated by scattering process going towards lower frequency, while for the same experiment, if you leave the coherent part at high energy, you can select processes which actually exchange energy from low frequency to high frequency, and you get correlations only in the part where the frequency out is larger than the frequency in. This is cross correlation, not autocorrelation, of course, because it's not symmetric. And you see how it evolves, that every phonon line evolves in time at its own frequency. But when this process gives you a positive correlation, this process gives you a negative correlation. And the process is heterodyne, so the line shapes are not, they are dispersive line shapes, but it's actually, again, it's not like the standard dispersive line shape, because what we are seeing here is the correlator. So it's not intensity measurement. I'm not sure I answered the question. I just wanted to make it, sorry, I took
yeah,
time, but I just wanted to make it clear. Yeah.
A little bit better.
Please help me if you see raised hands or So it looks like really, I mean, this coupling between phonons and or vibration in the molecular, from the molecular point of view, looks like this coupling between electronic degrees of freedom and phonons is really the let's say one of the topics to be explored in the future. And we have been seeing this subject in different way, with different flavors from different point of view. Really looks like we can really exploit this interaction, this vibronic coupling, right? At the end of the day, I would call that vibronic coupling to drive processes, to control processes, to shift observables, to I don't know, this is probably the message, right, we can get out of this session today, sort of summarizing observation. Is there any other question?
Where is it? No. I had a question. I don't find the hand here. Sorry. I try to raise my.
No problem. You can open the mic and speak.
It's to come back. It will again be for Daniele, but about this question of disorder, right? Because would you expect we see them if we have disorder? I'm thinking of quantum dots, but can also be different kind of Raman process that are due to effect of environment. But do you think if you had a coherent pulse, then could you see them in a correlation?
Yeah, your question triggered I've been thinking about it for the last half an hour. I don't have an answer, in the sense that so what I've shown in detail here is this using classical stochasticity. So basically shaping classical intensities and measuring correlations in this case. And if you if you use classical stochasticity, I think that in some sense, I'm still seeing ensemble properties, in the sense that I just see the correlation between classical quantities. But if we go to the quantum limit, because now we have developed a tool to try to do the same game, really going to the sub-photon level resolution in measuring the intensities. So just going in with a light pulse with, I don't know, 10 photons on average, and looking at the multimode correlations in this case. If you go at the quantum level, so you have a single photon, then my guess is that there must be a window there where you can go beyond ensemble properties, because one photon will be scattered by one dot. So in this sense, I think it's definitely worth to think about. I don't have an answer, in the sense that it's really, it's I don't have an answer.
But you would not think that you need to invert your scheme, that you would use coherent light, right? But your medium is incoherent, right? Just do in some sense. We always started with coherent light. So in this sense, we took a different approach from the ones that Shaul proposed of using, like non-classical light. We use coherent light, and we look at what happens to coherent light going through a nonlinear interaction process. So it's a little bit, we don't really use quantum light, but we observe quantum light, and we look at multimode squeezing. And multimode squeezing would tell whether the probability between two frequency components is independent or it is no longer independent. Mm-hmm.
And this is, so you start from a coherent state, so uncorrelated probabilities between all frequency components and spatial distribution, but you end up with something
where you may have instead two-mode squeezing.
Yeah.
And this would tell you something which is specific about the object which mediates this two-mode squeezing.
Yeah.
But yeah, it's definitely worth thinking about. Maybe we can keep in touch, and
Yeah.
it's I would be very interesting to try to formalize some experiment we can do, or I'll be very happy to discuss.
Yeah, that would be very interesting too.
I mean, since quantum light, right, was cited, Daniele was saying I didn't really use quantum light, but I did observe, right, quantum light. I remember discussions, I think it was 2 years ago, and in this Washington meeting, and Greg was one of the organizers, I think, right? And we were discussing about which was the future, right, of spectroscopy, and which kind of spectroscopy we could propose to have more observable, or have more, you know, I mean, have a progress, right, in the spectroscopy field. And I remember with Greg discussing about the possibility of moving to quantum light spectroscopy. What do you think, Greg, about that? Is it still a possibility? Is there an advantage to use quantum light? Is just a complication?
So we shouldn't kid ourselves that it's easy. So it is a complication. Let us lead with that. But at its heart, what spectroscopy is doing, especially spectroscopy with interactions separated in time, is using the material system to carry the correlation between the pulses. And that's fundamentally what Daniela was looking at, where you have a pump and then you wait a certain period of time. The ability to put such a correlation into your light field as well gives you the opportunity to look at very different processes and to understand correlations in time and space in a new way. And so I still see this very much as a frontier to get new information out of structured molecular systems. And so, I think, it's extremely important to look at how we do this. Like I find this experiment that Daniela was explaining to be fantastic. It's inspiring. It makes you think of new ways to probe some of these effects. And then Francois' question about how you move it to materials and quantum dots. I think there are a lot of possibilities there, because now the material itself may not be periodic and is disordered, but you can think about structured light fields. They could be classic, with two beams coming at different angles to create a grating across the system. And then you have a phase imparted on the disordered material that creates the order that you can then scatter off of. And there are lots of ways that you can begin to think about how you might expand these to other systems by moving some of the information in or out of the nature of the excitatory field. But classic light limits you, and quantum light gives you more opportunity. So there will always be an opportunity there. The question is going to be return on investment, because it's hard. It's truly hard. If we do the signal averaging that Daniela was talking about with pulses with 10 photons, that could be a very long PhD, unless you get very clever. And so, one has to do the back of the envelope calculation, figure out the right way to do it. So if you're a student in the audience, do the back of the envelope calculation. And if it comes out to me more than about 10 years, find a clever way to do it. There are opportunities there.
I have a question regarding this last discussion, but if we have this random noise that is introduced by quantum dots and materials, how we define the covariance? Like covariance is really inside the material, right? This covariance between what and what now we will look at.
Yeah, this is what would need to be defined. But the point is that covariance, you define it between two frequencies. So you would need to have an object which actually give you a correlated response at two frequencies. For instance, you have I can just imagine, I don't know the systems well, but it could be like an absorption at a given frequency which correlates with an emission at another frequency.
And then if you have a statistical ensemble where everything is absorbed and everything is emitted, so they overlap or whatever that you don't resolve, this correlation would tell you whether the photon emitted at one frequency came from another frequency or wherever it came from, right? So it's a
Yeah, it's not spectroscopy, basically, right? You correlate the excitation and emission, right?
yeah, but on a, let's say, on a single photon level. That's the point.
Mm.
It's not you do not you go around the statistical ensemble issue because you do it on one single photon if you can. This is
There's nothing that requires multiple photons for a nonlinear response, though that is how we typically think about it. You can get a nonlinear response from a single photon. And I mean, it actually limits the pathways because you don't have the excited state absorption pathway open to you. And this is something that Shaul has written about a bit, but also in Oregon, there's a group looking at fluorescence detected multidimensional spectroscopy. Andy, I'm embarrassingly drawing a blank on his last name. It'll come to me in a moment. Brilliant guy in Oregon. And it's a really neat thing because you can use single excitation photons to do multiple interactions. So I think this should be possible. The nonlinear response is in the material.
And as a chemist, I have to say this is, to me, I mean, very important because we can work on the material, right? As a possible starting point, because quantum mechanics, as Greg said, is there, right? So the response is there. So now it is a matter of being able of engineer in a correct way the material so that he does what we want to to obtain, right? This was very nice. I mean, that's really, I mean, really this discussion really, I mean, it was very worthy, right? To have this face to face with all the speakers together, all the people together. It was very interesting interactions. Now, I mean, we are officially, I mean, finishing our time. We can keep going, right? I mean, since we are in this Zoom, but I would not like to, you know, take too much advantage of the speaker's time. So I am asking if there is any other question from the audience. Otherwise, I let the speaker free. Thanking them again for the very nice talk and the very nice discussion. And thank you, Greg and Daniele, for your availability to be here to discuss with us, to share your ideas, to share your expertise with us. This was very interesting session, very successful session. And so let me thank you again and again for your contribution. Also, on behalf of all the organizer, all the COPAC network meeting. And I think if Françoise, I mean, there is nothing else to add from the COPAC side, I would thank again the speakers and close the discussion.
Yes, I
Invite all the people to join tomorrow to the second session.
Thank you, Elisabetta, as well, not only for the invitation, but your flexibility in moving this to a new platform where we could speak and interact. I really appreciate your flexibility on the fly to do that and do that well. Thank you.
Yes.
Thanks for putting this together. It's really, yeah. I'm a little bit an outsider to the field of molecular spectroscopy, but I really think that it's interesting. It's really like it was very useful, very nice. And I'll be happy to talk further if there are ideas to be formalized. Yeah.
Yeah. So, Yeah, I don't have anything to add. We hope tomorrow there will be less technical problems with the other platform. Then we have learned what we need, and thank you very much also.
Okay.
Thanks again.
Thanks again. It was a pleasure to host you guys, and I'll see you hopefully in person in a conference soon.
Yeah.
And thanks again to the speaker. Thanks to all the people in the audience. Thanks to students. I need to apologize with student that has poster session, because I've asked them to prepare, to be prepared also to share something in this round table, since it is already late. Maybe this can be done. Yes, Francoise, please.
Just one point, because what I learned from Webikeo exchanging furiously emails is that they have recorded the poster session because the poor presenter didn't know that we did not see them, I think. Something like that is what I understood. And I am trying, I asked Manu, and I think there should be another half an hour given by Webikeo where they can present. I don't know when it will be, but it seems to me they worked hard, and it's really not fair that they were cut like this and we will have to go and see recordings. And so we are going to keep you informed on that.
Yes. Okay. Thanks again for keep going, and even with these technical problems. And I'll see you all tomorrow. Thanks again to the speaker. It was very nice.
Yeah, thanks a lot, and have a nice day, Greg.
Again, bye, 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 thanks.
Thanks. Bye-bye.